Hey folks, welcome back to another video in this series on quick paper overviews. And so today I have two papers. One is about reasoning models, which is all the craze right now, and the other one is about small language models. So let's get started. So this paper came out, this simple test time scaling, which has been making the rounds recently, and it is quite interesting because they show that all you need to improve the reasoning capabilities of your model is a data set of 1,000 questions. So what the authors of this paper do is they curate a data set made out of 1,000 questions. Like they curate, like they start with a standard test bank, and then they'll generate reasoning traces using Gemini models and so on, and only keep in like the select few, like ensuring they have a good diversity and so on. And then they perform like fine tuning only on this. So they take an already good model, which is this Quinn 32B instruct model, which is already pretty good. They fine tune on this 1,000 data. And then with this, they see quite a remarkable improvement. So that's one thing. The other thing is they do this thinking budget enforcement. So the other thing, test time scaling. So what they do is so let's see. Right, so budget forcing. So what they do is they monitor the decoding tokens, and if they want to stop thinking early, they will just directly inject this token, like or they will inject an end of thinking token so that the model has to stop thinking. Even though its thought process hasn't been completed, but half a thought is already good enough for these models to solve the problems. So that is one way. And for let's say you have a longer budget and you want the model to continue thinking, then they inject a weight token. So for example, here in this case, the model is thinking about, so the standard question, how many R's in a strawberry, the model starts thinking about it and it comes to a wrong answer. Then they know, because they have more thinking budget, they will inject the token weight, or wait, reminiscent of DeepSeek. And then the model will just rethink, because these models are used to like reevaluating. They're very suggestible. So then the model will try to like rethink, and then it'll come to a correct answer. So the interesting things in this paper are two. They train a model with like high quality data, one thing. The other thing is this, they do this budget enforcement, thinking budget enforcement. And they see, like the more you let a model think by appending weight to force it to go, the benchmark performance scales up and it improves. So this is interesting, and this is kind of different from like what the MCTS kind of strategies, where you do like a parallel polling and you do majority and so on, where you hit a plateau, versus this like output token scaling, like in terms of just sequentially going down, like because the model will take a wrong path, but then again it will backtrack, because with this weight token it can like fix its mistakes. And that's the idea, and that's what this short paper is about. So they have like one of the samples of the among the 1,000 that they've trained, and it has, so this is the question, this is the solution, and then they have an insane amount of reasoning trace. So anyway, yeah, that's just one thing. So pretty cool, pretty cool, pretty cool. The other paper that I want to talk about is it's a small language model made by the Hugging Face team, which is also interesting. It's interesting because they go into some nice details about pre-training models, which I wanted to highlight. I mean, small models, fine, good. They're not pushing the boundaries here, but it's still a good model. It might be pretty good in the benchmarks as well, but I like the fact that the paper talks about a lot of interesting things. So, for example, they say they trained the model on, they overtrain the model on 11 trillion tokens. So first of all, how do you identify what are the good data sets to use, right? What are the bad data sets? So for that, what they would do is like they'll start with a checkpoint. By the way, their model is 1.7 billion parameter, and they'll take this checkpoint, and so what they do is so they train the model on, let's see if I can find it. Right. So randomly sample 350 billion parameter tokens. So they'll have a checkpoint which is trained for, um, 350 billion tokens at a constant learning rate. So they have that, as a checkpoint. Now, for example, a new data set comes their way. They want to check how good that data set is. What they would do is they would run an annealing experiment. So what they will do is they will randomly decay. They will run a ramp down training. That means they will train on the model and then let the learning rate decay to 0 on that data sets, because you're trying to hit a local minima, and see how well it does with the different data sets. That's their strategy. Yeah, so yeah, this annealing approach, the learning rate linearly decays to 0 while training on the mixture. Now, for different data sets, you want to start at a different checkpoint. So for math and code, because these abilities emerge later, you want to start at a later checkpoint. So they do this annealing ablations at 3 trillion tokens, but for others they do it early, and so on. So so it depends, like where you want, like where you want to perform the ablations depends on like what capability you're looking at. Beyond that, what they also do is, right, so they have a lot of coding data, and the pre-training stage they do in like these. So pre-training is always done at a constant learning rate. Once you warm up, you do it at a constant learning rate, and this is their strategy for the constant learning rate. So for the stage 1, for the first 6 trillion tokens, they're knowledge heavy. Next 2 trillion tokens, again knowledge heavy, but then they add a bit of, like, they include the proportion of math. And we've seen that the better your model is at code, the better it will be for math as well. There's some proportionality there. And then in the later stage, because now you're building up that math capability, then you start ramping up that math knowledge. Yeah, so that's what they do. And then then there's a final decay. So then they will then they extend the context length. So you have a pre-training stage, which is done at a constant learning rate and a constant context size. Then they expand the learning rate by doing this long context fine-tuning, or it could be pre-training as well, where they extend it to, let's see, 2K to 8K. And yeah, and then your instruct tuning, your reinforcement learning, and so on. And we see that this model performs like really well. It beats the other smaller models of the same size. Well, it's slightly bigger compared to this and this, but but still, it's pretty cool. And the fun fact is, like, they have their own code base for training this model. So Hugging Face has a repository, which is also something I wanted to point out. Let me see if I can like find it. Let's see, it's called Nanotron. Right. So they train on like 256 H100s. So that means what? 16 machines. And yeah, so they have their 4D parallelism framework, 4D or 3D. Yeah, so I guess 3D parallelism framework, which they've built. One of these days, I'll take a look at this code base as well. Seems interesting. But yeah, so that's all I wanted to talk about. Interesting paper. Take a look if you want to learn about some details of these like how pre-training works, and also the rough ideas are the same. They would also translate to like bigger models. So that's why this might be interesting. But in any case, I think that's it for this video, and I will see you guys again next time. Cheers.